Well, good morning. Let's see. Not a lot of people here today, but that's okay. I'm going to introduce the ideas of adding velocities today, and I'm just going to switch immediately over to my shared screen there. And so we'll dive into that, unless you happen to have a question already or about something that's popped up. Let's see, I still need to get the materials posted for the projectile motion lab. I made the film yesterday, but I can't remember if I've uploaded that one to YouTube yet or not. Anyway, that'll be showing up this afternoon, the material for the lab this week. And I think, yeah, you're going to be in the lab group with the people who usually show up to class. So Ty, Jenna, and Ben. So more about that later. Let's see. Yeah, just dive into what we're going to be doing today. I'm not crazy about the way the book happens to introduce the idea of adding velocities. And so I'm going to deal with it in a little bit different way. So let's imagine that we have somebody who is on some kind of a, I don't know, like a flatbed railroad car. There are such things. And this flatbed railroad car is moving in this direction at, I'll call it V sub C, and I'll put an arrow on it. Not that it matters a whole bunch, but the velocity of the car might be something like, say, 20 meters per second, and it's going to the east. So that way, if I state its direction also, we can call it a velocity. And then on this railroad car, there are two people, and I'll sort of draw them in an odd way here, but they're playing catch with a ball. And let's see, there's the mitt of one of them that they'll catch the ball in. And this person can throw the ball to them, and it'll travel there. And the velocity of the ball, when this person throws it to this person, they can also throw it at 20 meters per second. Except I'm going to put a plus or minus on that one, because if this person throws it to this one, it'll be going east. But if this person throws it back to this one, it'll have a minus velocity in the east direction because it's actually going to be going west. So, and they're both on this railroad car that has wheels that's going that way. And then there's somebody who's standing here on the side of the track, and they're looking at these people playing catch with the ball. What's the velocity of the ball relative to this person who's standing here? Well, when the person here throws it in that direction, the velocity of the ball will end up being 20 meters per second eastward relative to the car. But you add to that the 20 meters per second east that the car is going, and it'll actually be 40 meters per second east. You add the velocities that way. When this person throws it back that way, the car or the ball is going 20 meters per second relative to them in that direction at the same time that they're standing on this car that's going 20 meters per second east, and it ends up being a 0 meters per second relative to that person. There's another way that you can understand this. I don't know if any of you, however many people, we're up to our usual, have ever been in an airport that has a moving sidewalk. And these moving sidewalks typically move along. It's like this giant conveyor belt is what it is, that is here, and it loops underneath here and then comes back. But they'll be real long. They'll be 100 yards long or something like that in an airport. And they go, I'm guessing, maybe 3 miles per hour in some direction. And I don't see this so much. I haven't flown recently, but used to be, you'd get on one of these things and you could walk. And if you're walking at 3 miles per hour with respect to the thing that you're standing on, you would actually be going about 6 miles per hour relative to somebody who's standing over here on the side. So you'd get something like that going on. But a lot of times you'll see parents trying to keep their kids entertained at the airport, and the kids will see that moving sidewalk and they'll go over there and get on the thing. And so you'll have this very small person on it who might be going in this direction, and they find out that if they run with their little short legs at 3 miles per hour in that direction, that they can stand right next to their parents, not move relative to their parents who are standing by the side of this moving sidewalk. And that's something that can happen. Velocities add as vectors in this regard. And so I find an easier way to express these things is to think of a fixed reference frame or a fixed place. We can think of it that way. And that would be just like the floor of the airport. And then there's a moving place. Fixed place, airport floor, or I guess it's airport terminal floor. And the moving place is the surface of the moving sidewalk. So we would have that. And then we'll have an object, which will be something that can be moving on the moving sidewalk. So we've got all these three different things that we have to think about. And if I define a few things, I'm going to call VO/M, and this will equal, now I'm going to be putting arrows on these eventually, but for now I'll just leave them off. This is the velocity of the object with respect to the moving sidewalk. And then I'll have a velocity of the object with respect to the floor. And so that'd be the velocity of the object relative to the fixed thing. And then I'll also have the velocity of the moving sidewalk with respect to the floor. Whoops, of object. I got to thinking and forgot to finish this. Velocity of the object with respect to the floor. And then I've got the velocity of the moving sidewalk it's a whole lot shorter to just state these in words, but I think I need to write them out this time. Velocity of the moving sidewalk with respect to the floor. And what I get is that the velocity of the object relative to the floor, the fixed floor, will equal the velocity of the moving sidewalk with respect to the floor plus the velocity of the object with respect to the moving sidewalk. And this seems pretty abstract, but if you imagine it here, the velocity of this person who's walking on the moving sidewalk with respect to the floor, well, they're going 3 miles an hour on the sidewalk at the same time that the sidewalk is moving to the right at 3 miles an hour. So their velocity with respect to the floor is the sum of their velocity with respect to the sidewalk plus the velocity of the sidewalk with respect to the floor. They add that way. And this is a way of stating that mathematically. If I define a direction to be positive, if any of these velocities happen to be negative, like if they're going the opposite direction on the moving sidewalk, then this term becomes negative. And that's the case of the little kid on the moving sidewalk that'll be going as fast as their little legs will take them and just standing still next to a parent next to them. You can do the same thing on if you ever go down an up escalator, you can be stepping down the up escalator at the same time that sometimes there's staircases right next to escalators, and you can be at rest with respect to a person standing on the stairs if you're stepping downward on the up escalator. So the same kind of an idea there can happen. So that's the idea. And we could also extend this and put arrows on this thing and actually have directions going on as well. And so that's what we'll try to do when we go through a few problems having to do with this. So let's try one out. And we'll start off with what seems like a two-dimensional problem, but it's really kind of a one-dimensional problem. I don't know if I have any flight students in here, but this is something that people who fly have to take this into account. If they're flying through the air, their velocity with respect to the ground is equal to their velocity with respect to the air plus the velocity of the air with respect to the ground. And so you can end up with complicated things happening in that case. But in 1979, Brian Allen pedaled a human-powered aircraft across the English Channel from the cliffs of Dover to, I have no idea how to pronounce that. I'm guessing it's like Grenay or something. Often in French, the final syllabuses are silent, but don't know for sure. Anyway, he flew for 160 minutes at an average velocity of 3.53 meters per second in a direction 45 degrees south of east. Now, this would be his velocity with respect to the Earth. And so that's what we'll need to think about here is that. Now, let's see, I'll sneak this under here so I don't write it. If I just make a sketch of what he was doing, here's his velocity. Let's see. I'll just call it the velocity of Brian with respect to the Earth. And I'm told that he makes an angle 45 degrees south of east. So this would be east. And on a compass thing, this would be south. And his speed, VB/E, was 3.53 meters per second. So not huge. But he flew for 160 minutes at that time. Well, if he's going in the same direction all the time, I can figure out the magnitude of his displacement. The distance that he would travel during that time is just going to be his magnitude. This has no arrow on it, but if I tag on something, actually I could do this. His distance traveled is going to be that magnitude times the time that he flies for, and it's going to be 45 degrees S of E, south of east. And by stating the direction and the magnitude of the displacement, I turned it into a vector. Now, what about that time? Well, T is equal to 160 minutes, but I've got a velocity in meters per second, so I'm going to have to multiply that by 60 seconds per minute, and I'll end up with seconds. And it's about quite a few. 9.6 times 10 to the third seconds, 9,600 seconds. Wow, that's a lot. Anyway, so the displacement will be this thing times the VB/E, so 3.53 meters per second times 9.6 times 10 to the third seconds, and this will be 45 degrees S of E, which ends up being, let's see, and I get 32 significant figures, 34,000 meters south of east, or that would actually be 34 kilometers, which is the way they would measure it over there, they being metric countries both. So 34 kilometers south of east would be his displacement in there. And I did it here because this didn't leave me a whole lot of room up here. Now, it says he encountered a headwind averaging 2 meters per second, almost precisely in the opposite direction of his motion relative to east. So he was overcoming a 2 meter per second headwind. Now, I can treat this part kind of one-dimensionally because he's going this way, the wind is going that way. He'd have to be going that direction relative to the air. Well, the air is going that direction relative to the ground. And so I can treat this as a kind of one-dimensional problem. His velocity, this is the velocity of Brian with respect to the Earth, is going to equal the velocity of Brian with respect to the air plus the velocity of the air with respect to the Earth. So I've got the velocity of the object, that's Brian, with respect to the fixed thing, is going to equal the velocity of Brian with respect to the moving thing, which in this case is the air, plus the velocity of the air with respect to the fixed thing. And so this is like the train car moving with respect to the Earth, except in this case it's that. And if I think of the positive direction as the 45 degrees south of east, Now, we happen to know velocity of Brian with respect to the Earth. That's the 3.53 meters per second. And that'll equal the velocity of Brian with respect to the air plus the velocity of the air with respect to the Earth. It's actually blowing in the opposite direction. That'll be our minus direction here. So plus a minus 2.00 meters per second. And it means that the velocity of Brian with respect to the air is going to equal the velocity of Brian with respect to the Earth plus 2.00 meters per second. Okay. Whoops, and that one's the 3.53, because when you bring it to the other side, it changes sign. And that ends up being this thing, which is that, plus 5.53 meters per second. And if I want to stick an arrow on it and call it a velocity of Brian with respect to the air, this is his airspeed, is the way that's often referred to as, but it would be the 5.53 meters per second, 45 degrees south of east. So that's his velocity with respect to the air. Well, what about his total displacement relative to the air mass? How far is that? Well, it's going to be that velocity times the same time that we had over here. So his displacement of Brian with respect to the air now is going to equal his velocity with respect to the air times the time. So 5.53 meters per second times the 9.6 times 10 to the third seconds. And direction-wise, it's 45 degrees south of east. And it's quite a bit farther. I get 53,000 meters south of east, which is 53 kilometers south of east. So he actually had to fly 53 kilometers through the air instead of 34 kilometers through the air because of that wind that was blowing against him. If he'd flown on a calm day instead of landing in whatever it was, Cape Grenade or something, that's a wild guess, he would have flown 20 kilometers past it. So, or 19 kilometers past it anyway. I had an interesting experience one time having to do with a plane flying through air. We were driving back from Spokane one Sunday afternoon. We'd been in town for a family dinner, in Spokane for a family dinner. And we had it, at the time, we had a Plymouth Voyager, which was a kind of the low budget version of the Dodge Town and Country minivan. And it was a 1988 one we bought then. And it had a 4-cylinder engine in it. It would, when we first bought it, the speed limit on most national highways was still 55 miles an hour. They lowered the speed limit in the 1970s during an energy crisis or an oil crisis that happened back then. And it would get 30 miles per gallon for a minivan when you were going at 55 miles an hour. But then as soon as we get to Washington, the speed limit gets raised to, I think it was 65, but it didn't have a very powerful engine. But we're driving back from Spokane and the wind is blowing like crazy out of the west. And air resistance is the main thing that you have to overcome in a car. And when you've got a van with a 4-cylinder engine, it was struggling to go 65 miles an hour. But there was an airplane that was flying, oh, it was at a pretty low altitude, just above the freeway. And the airplane's having to fly through this this air too. And so down here on the ground, we're putting along at 65 miles an hour. And that's our speed relative to the ground. And I would guess that day that the air was probably blowing at least 40 miles an hour, maybe more. But there was an airplane up there that was one of those old kind of float planes. And they've got a lot of air resistance because their landing gear is basically these big pontoon things that they land with on lakes. Whoops. And anyway, this plane, I don't know, its airspeed may have been a little over 100 miles an hour, but the air was blowing that way opposite it. And so its speed relative to the ground was actually less than 65 miles per hour. And there was a long straight stretch of I-90 that when we started it, this plane was maybe half a mile ahead of me. And after 10 miles or something like that of flying in this straight line, I passed this airplane. So I passed an airplane in my car. That was pretty amazing. Not something that you get to do, but that was a relative motion situation that we were in, or in addition of velocities. The velocity of the airplane with respect to the ground was equal to the velocity of the airplane with respect to the air plus the velocity of the air with respect to the ground. And if positive is that direction, this was a big negative for this day. So maybe this was 100 miles per hour. But if this was negative 40 miles per hour, you end up with this airplane only going 60 miles an hour with respect to the ground. So that was kind of neat to do that. All right, now we'll take a look at this. A science student riding on a flat car of a train traveling along a straight horizontal track at a constant speed of 10 meters per second, which isn't very fast. The student throws a ball into the air along a path that he judges to make an initial angle of 60 degrees with the horizontal and in line with the track. The student's professor, who is standing on the ground, observes the ball to rise vertically. How high above the student's hand does she see the ball rise? Good grief. This seems like one of those questions that's, it's like the place where everybody on the island is either tells the truth or is a liar, and you're supposed to figure out what color hat they're wearing. So I mentioned that the other day. Those are fun riddles to try and work through, but it's not. We're going to be combining a few different things here, but let's start with a picture. So we'll have this railroad car here, and I'll draw its wheels first. Whoops, missed. That's okay. And let's suppose that the railroad car is going this direction at 10.0 meters per second. Okay. Then we have a student on the car, and they throw a ball into the air, and the ball initially makes an angle, they think, of 60 degrees. 60 degrees with the horizontal. But somebody who's standing here at the side of the tracks would perceive the ball as just going straight up and coming straight down. Now, we can write this as we'll have the velocity of the ball with respect to the Earth. So B/E is going to stand for ball with respect to, WRT is the way I abbreviate with respect to. I'll also have ball with respect to the student. And then I'll have, let's see, whoops, S/E. That's the student with respect to the Earth. So I'll have these three different velocities here, and I'm going to put arrows on top of them this time. Okay. This will be the velocity of the ball with respect to our fixed thing. That will equal the velocity of the ball with respect to our moving thing. The student is standing on the flat car, so they're our moving thing. They're attached, we can think of them as being at rest with respect to the flat car. So there's the velocity of the ball with respect to the student, plus the velocity of the student with respect to the Earth. And so I think I can draw a triangle that will illustrate this. Yeah, where's my ruler? There's a ruler. First of all, the velocity of the student with respect to the Earth is going to be horizontal, just like that. Now, the student throws the ball so that they think it makes a 60-degree angle with the horizontal. And so I'm going to do a vector addition problem. Remember when you add two vectors to each other? By the way, vector addition is commutative. So I could imagine the VS/E first and the B/S first. You can add things in either order and you still get the same thing. But velocity of the student with respect to the Earth whoops, I was drawing on top of the ruler and not anything else. This is the velocity of the ball with respect to the student, and it makes a 60-degree angle. And they add together in such a way that the student's professor sees the ball just going straight up and then coming straight down again. But initially, the student's professor would just see the ball going straight up. Okay. So this is the velocity of the ball with respect to the Earth, which the professor is standing on. So the student throws the ball in such a way that the horizontal component of the velocity of the ball exactly cancels out the velocity of the train with respect to the Earth. So, and in this triangle, we've got we have a right angle down here, and we happen to know how big this happens to be. So from that, I should be able to figure out the velocity of the ball with respect to the Earth. This would be the initial velocity of the ball with respect to the Earth. So just make a quick sketch here. 60-degree angle there, 10 meters per second here, right angle there. I can figure out what this is. This is the velocity of the ball with respect to the Earth, the initial velocity of it. And then it becomes a projectile motion problem. a ball goes straight up with an initial velocity of whatever it is I'm going to figure out, and how high will it go? So that's the idea. Now, this is a trig function that we have not used yet. The velocity of the ball relative to the Earth divided by 10 meters per second, that's the opposite side divided by the adjacent side. We haven't used that yet, but it's the tangent. So the velocity of the ball with respect to the Earth divided by 10 meters per second is the tangent of 60 degrees, which means the velocity of the ball with respect to the Earth, I'm going to get rid of my drawing and center this here, it can work better, is going to equal 10 meters per second tangent of 60, which is 10 times tan 60, and I bet I'm going to get some weird, 10 times the square root of 3, which is actually 17.3 meters per second. Now, it was 10.0. So I can keep 3 significant figures. It's also 60.0 degrees. That was kind of sloppy of me. I should always try to write the correct number of significant figures in my solution. So anyway, 17.3 meters per second was the initial velocity upward. So how high up will it go? Well, now we can use some projectile motion problems, but the one I think I'm going to use is the one that doesn't involve time. I don't think I've done that yet for you, but here's something you can say. This is one of our equations for it. V sub y squared is equal to V naught y squared minus 2g times y minus y naught. Okay, this will represent y naught is how high the ball is when it leaves the student's hand. Y will be its final position and something that happened. So y minus y naught is how high above the student's hand the professor will see the ball rise. So, okay, so that's what we're after. And when the ball reaches that point, its v sub y is 0 because it stops up at the top. And so this is 0, which means we will have, if I bring this to the left side, I'll have 2g times y minus y naught is going to equal v naught y squared, or y minus y naught will equal v naught y squared over 2g, which is, v naught y is our vb slash e. So this just happens to be the form that it takes on your formula sheet, but this is what I called it here. Okay, which is going to be 17.3 meters per second squared divided by 2 times 9.81 meters per second squared. So the height that the ball rises to, this was a harder problem. Often a problem like this would just stop with asking what was the initial vertical component of the ball's velocity, which is what we found there. So we have to do more here. Let's see. Can I square that? Yes, I can. Oh, let's see. 300 should be around 15 meters, and it is. Okay. 15.3 meters is how high that thing happens to go. So this was kind of a tricky problem. Let's see how bad the rest of these get. I didn't leave enough room on any of these to do them, but I think we can do it. Car travels due east with a speed of 50 kilometers per hour. Rain is falling vertically with respect to the earth. The traces of the rain on the side windows of the car make an angle of 60 degrees with the vertical. Find the velocity of the rain with respect to the car and the earth. Now, this is one of those things that is easier to find by making a good picture first instead of just an equation. So I'm going to start off with the assumption that east is this way. And so I have this car that's headed east. And so here's the velocity of the car with respect to the earth. And it's 50 kilometers per hour east. So it's that. So V C/E is 50 kilometers per hour. And then, let's see, I have the velocity of the rain with respect to the earth. We don't know anything about that. It's unknown. And kind of built into here, we'll have the velocity of the rain with respect to the car, which we don't know. Let's see, if I stick directions on these, unknown but down. This is the velocity of the rain with respect to the car, unknown, but at a 60-degree angle. So this is kind of a weird problem. We happen to know one of the things, one of the velocities and its direction. The other two, we don't know the speeds, but we do know their directions. The rain is falling straight down. And to somebody in the car, it looks like it makes a 60-degree angle with the vertical. Well, a 60-degree angle with the vertical, oh, and the equation I can write here, I guess I could put arrows on each of these, is that the velocity of the rain with respect to the earth will equal the velocity of the car with respect to the earth plus the velocity of the rain with respect to the car. Okay, this is the velocity of the object with respect to the fixed frame. This is the velocity of the moving frame with respect to the fixed frame, car with respect to the earth. This is the velocity of the object with respect to the moving thing. So what do we know about these? Well, the result of adding these two things is something that's straight down. So I can draw a picture for that. Velocity of the rain with respect to the earth. And let's see, 60-degree angle with the vertical for somebody in the car, but this thing plus this thing has to equal this. So here's my vector addition problem. This is the velocity of the rain with respect to the car, and it says it makes a 60-degree angle with the vertical. Okay, well, if this is a 60-degree angle, that makes this a 30-degree angle. That makes this another 60-degree angle. So what can I figure out from that? I need to draw a new picture. One that just has those things in it. Okay. Here's the velocity of the car with respect to the earth, which is 50 kilometers per hour. This is the velocity of the rain with respect to the earth. This is the velocity of the rain with respect to the car. And this is a 60-degree angle this was 60 degrees too. Let's see, in that case, these might be alternate interior angles. I'm not sure. I forget the geometry term for those things, but anyway, this is a right angle. And so if this is 60, that's 30 degrees. So I've got a 60-degree angle there, and I think I can use my tangent function again, or I could use my tangent function on this angle. I can say that the velocity of the rain with respect to the Earth, opposite side divided by adjacent side, divided by 50 kilometers per hour. Well, this is the side opposite. This is the side adjacent. Opposite over adjacent is tangent. So that's the tangent of 30 degrees. So the velocity of the rain with respect to the Earth is 50 kilometers per hour, tangent of 30. I'm just going to calculate it rather than write it out here. Tangent of 30. Oh, 50 square roots of 3 over 3. That's practical. About 29 kilometers per hour is what that is. Then it also asks, what's the velocity of the rain with respect to the car? So it asks for that. Well, in that case, let's see. I can do this. This is a perpendicular angle. This is the side adjacent to my 30-degree angle. This is the hypotenuse. And adjacent divided by hypotenuse is the cosine of 30 degrees. So let's see. That tells me that 50 kilometers per hour, the adjacent side to that angle, divided by the velocity of the rain with respect to the car, adjacent over hypotenuse is the cosine of that angle, cosine 30 degrees. Let's see, be careful on a problem like this. Don't try to immediately solve for this. First, multiply out from underneath by this, and you will get 50 kilometers per hour is equal to the velocity of the rain with respect to the car times the cosine of 30. Or finally, you'll end up with the velocity of the rain with respect to the car, divide both sides by the cosine of 30, and that will equal 50 kilometers per hour divided by cosine of 30 degrees, and you get about 58 kilometers per hour. So the velocity of the rain with respect to the car is greater than the speed of the car because you've got that vertical component that you add on to it. Okay, the next problem I probably won't have time to do, but it's kind of neat. It's called the aberration of starlight. And let's see, it looks like I used up most of it. But in its path around the sun, the Earth is traveling at 2.98 times 10 to the 4th meters per second. If a telescope is aimed in a direction perpendicular to the Earth's orbit around the sun, by what angle would a star's light appear to change due to its motion? Well, this is kind of interesting. So you have this vertical telescope here, like this, and it's attached to the Earth. So it's actually traveling in this direction at 2.98 times 10 to the 4th meters per second. And then way up here, there is a star, and the light from that star is presumably coming straight down because we've got the telescope aimed straight up. But we're going to end up with, this is the velocity of the light with respect to the, I'm going to say, boy, let's see, this is the velocity of the Earth with respect to a fixed frame. Actually, it's not such a fixed frame, but we'll say that it is. Velocity of the Earth with respect to a fixed frame. This is the velocity of the light with respect to a fixed frame. And we would like to know what's the velocity of the light with respect to the Earth. So now we happen to know the velocity of the light with respect to the fixed frame. It's the velocity of the light with respect to the Earth. If I try to draw this picture, velocity of the light with respect to the fixed frame, let's see, is going to equal the velocity of the Earth with respect to the fixed frame. Sorry about the notation, plus the velocity of the light with respect to the Earth. And this is supposed to be an L here. Yeah. Okay, well, I can draw a picture of that at least. Velocity of the Earth with respect to a fixed frame is going to look like this. In order to get the velocity of the light with respect to the fixed frame being down like this, I have to have the velocity of the light with respect to the Earth being up like this. I'm not going to do the math on this. It ends up being a pretty small angle, but this is the velocity of the light with respect to the fixed frame. And arrows on all of these. However, what it means is that instead of looking straight up in their field of view to see this star right in the center of it, they have to look at a slight angle to it. And it's really a small angle, but this observation was actually the first observational evidence that the Earth traveled around the sun. All of the other observations that had been made up until that time, you could explain away with the idea of the sun being fixed and the sun moving and the planets doing various weird things. But this particular observation was the first convincing evidence that the Earth traveled around the sun instead of the sun traveling around the Earth. And so it was made, sometime I think in the late 1700s. I just read about this recently. And up until that time, the Copernican model was developed in the 1500s, and that was the idea that the Earth traveled around the sun. But it wasn't until, about 250 years after that, that this observation was finally made, and people could believe that that was the case. Although by that time, Isaac Newton had come along and done a pretty good job, and before him, Johannes Kepler had as well. So a little bit of astronomical history there. Okay, these things are kind of tricky. I am not going to be putting one of these on this first test that we're going to have, but the relative motion is something that can show up. In this class, I just like to introduce you to the concept a little bit. Tomorrow we'll have a review for the test. I'll put up some material. What I usually do is give you a sheet. I already put up on Sapling a whole bunch of review questions, so you'll have those things. But I like to give you a sheet that just has kind of a list of topics, and then I'll give you the test that I used last year in the class, a copy of it, or make that available to you anyway. And so tomorrow at regular class time, we'll have a review session. And come equipped with questions. I'll try to get the stuff posted later today, like the last year's test and the list of topics. And try to look at those ahead of time, so if you have any questions on them, you can ask them during the review session. If there's some, and look at the things that are on Sapling too for that extra credit review problem thing. See if there are any problems that you struggle with, and tomorrow's your chance to ask questions about those things. So we'll go on from there. Any questions right now or not? All right, I'll be getting stuff posted here later today.